Well, welcome to Microsoft. My name is Clemens. I work here. I'm usually in Germany, but I flew here to talk to you. I'm the architect for the messaging services inside of Azure. There being Azure Event Grid, Azure Event Hub, Azure Service Bus, Azure Relay, Azure Stream Analytics. That's also part of this. So we own those messaging services. We're also building the foundation parts of things like IoT Hub, which is kind of built on top of Event Hubs for the most part. And we're also providing the foundation for many other Azure services. So that's the thing we do in our team. And I'm also in that team responsible for standardization. I'm the chair for the AMQP technical committee in Oasis. I'm a member of the MQTT technical committee in Oasis. And I'm also the architect of the CNCF Cloud Events project. So what I'm going to talk about today is effectively event-driven architecture, but with a different name that I like a lot. There's a book by James Urquhart called Flow Architectures, which is a great high-level summary of things that are going on in the industry. And he speaks of flow architectures as a bit higher-level term compared to event-driven architecture, and why that makes sense, I'm going to explain in this talk. Of course, I've been told to put this slide here and to the end, because of course my annual bonus directly depends on the score. And so therefore, I would ask you to only give me good ratings, and if you hate me, then please don't rate. Thank you. So, you have all seen this picture. I've been super amazed by it. This is from the James Webb Space Telescope. Just for you, if in case you don't like this talk kind of in the beginning of it or in the middle of it, don't walk out, because I'm going to talk about this James Webb Space Telescope later, but not yet. So that's kind of the cliffhanger for about 2/3 of the talk in. So stay. All right. What are flows? What are jobs and signals and streams, event streams? Why do we do certain architectural things? So this is a conceptual talk which tries to create a bit of a terminology framework around what we're dealing with in terms of events. And I'm lucky to have a job where I can think about all that stuff for every day. So I'm hoping that framework, the terminology here, will help you. I also had on the start page a GitHub repo URI, which I'm going to show you later again, where I have a terminology set in the README and a ton of links and resources related to eventing and messaging, not only products, but also standards and intros, etc. So when we talk about events, we typically talk about something that happens. An event is a manifestation of an occurrence somewhere. Something happens, you capture that fact, and then you make that known. That's what an event is at the source. Something happens. Some might not care, right? There's tons of events happening that nobody cares about or nobody takes direct action on. So you are interested in that event, and then you are taking action or you are taking indirect action. So some might not care, some do something based on this. So that's the foundation for publish and subscribe messaging, PubSub. You publish events in case someone might be interested in them. And then if someone is interested in them, they will go and subscribe, and then they will do something based on it. There are two general kinds of flows when we talk about asynchronous programming and asynchronous stitching together of systems. There are event-driven flows and there's imperative flows. An event-driven flow is about observing things that happen, then deciding that you may want to go and take action on it, then you do act on it, and then you might tell someone else. In imperative flow, you listen to someone to tell you something, then you obey that command, then you execute that command, and then you respond. You notice that there is a difference here in terminology, and that is, in event-driven flow, you're volunteering to do work. You're volunteering action. Nobody's telling you what to do, but rather you observe what's going on, and then you yourself decide that you want to go and do something about it. In imperative flows, you're being told to do something and then report back. That difference, even though we're talking about effectively the same things here, has architectural consequences. Imperative is this. There's the boss, and the boss says, you do this, and you do that, and you do that, and you do that. That's a workflow. Predetermined, the boss knows it all, and the boss has people execute, right? There's a coordinator, there's an orchestrator, something has a plan, a program for how things are being executed, and then it goes to the workers and has things being done. Imperative. That imperative flow might quite well be, and in the real world, when we talk about people interacting, is practically always asynchronous. So asynchronous communication, right? Do something, and when you're done with it, then let me know. That's asynchronous communication. That is not necessarily event-driven, decoupled. That it's not the same. So this is imperative. An event-driven flow is different. An event-driven flow, the boss says, it would be nice if the following thing happened. And then the scientist says, okay, how are we going to go and do this? Maybe, well, I have an idea. And then the machinist says, hey, okay, so that's an interesting plan. So I'm going to go and try this proposal. And then everybody's kind of reacting on the ideas that everybody else has and kind of volunteers their work. Of course, it's a metaphor. It's not necessarily that it happens that way. Certainly not in engineering, but these were the icons that I had. So it's different. So there's a difference here. This is not a predetermined flow. There's effectively people are volunteering their work, and if you are thinking about more a volunteer organization, more like collaboration that you would do kind of in a hobbyist environment, that's kind of how things work more than they are kind of at work in an imperative flow. I just want to give you kind of that as a mental model, as some help to understand what the differences are. So imperative is all predetermined. Event-driven is more everybody's volunteering into the effort, which also means that all these different activities become exchangeable. You can also do two acts based on one event. Okay, so some terminology that comes out of this, the consideration. In an imperative flow, you have an execution plan with predetermined actor roles. The work is assigned, executed, and completion is then reported. Changes and extensions require modifying the entire execution plan, and it's really for command and control. In event-driven, there's no predetermined execution plan or actors. When you raise the event, you don't make a plan for what's supposed to happen with it. The work is volunteered. It's basically attached to the system. And then changes and extensions are local to actors, right? They don't necessarily, nobody's depending on them, except their downstream dependence, which then depend on events that they raise. And that allows for more dynamic collaboration. What that factually means, so most complex systems have both of those things. I'll give you an example. Imagine you're building a customer relationship management system, an ERP system, any of these sorts of applications. Most of us can go and relate to them. There is usually for each module, there's a very predetermined flow of how objects are being edited, right? There's a shipping address, and the shipping address has a bunch of predetermined fields, and you go and create a new one, you delete it, you update it, you do operations on it. That's all predetermined. But you can then raise an event that says the shipping address has changed. And now someone can go and say, hey, when the shipping address has changed, I can go and hook some activity on it, which will then go and send a letter and say, oh, welcome to your new home, something like that. But as you will notice that when you actually move home, then you suddenly get a whole bunch of trash in your mail. That's kind of one of those events. So there are event-driven is for extensibility often, and these imperative flows are often for the core of the application, predetermined flows. Both of those things coexist. I'm against architectural extremism, which means that usually you don't build applications with a single paradigm. So saying everything is always event-driven is nonsense, but everything is always RPC imperative is also nonsense. Typically, systems have a good mix of both. I'll give you an example. This is my football club. So my heart is there. We're in America, soccer club. So Borussia Mönchengladbach is placed in the first Bundesliga in Germany, and I am on the digital advisory board for that club, and had the pleasure to help with the ticket management system, which they redid in the pandemic. The prior ticketing system was pretty terrible, so we decided to do everything with SaaS and PaaS. And we found a SaaS provider, and luckily they have a really nice event-driven API. So their API is not imperative, you don't call them, but they actually give you an open API document and say, go and implement these event handlers, which is spectacular. It's exactly like that was, I saw this and I'm like, wow, you've done a really great thing here. So this is how this works. There's the ticket portal, which is now realized by Eventim, so that's up in the right corner. That's realized by a company called Eventim. They have this API. They give their partners this open API document and say, go and implement a web service using the open API. And what they then do is whenever something, and then they configure this, and whenever they sell a ticket, or when they make an update of customer data in their portal, they will raise an event, and that event is then being caught by us. We're implementing the API. We then put that message into a queue. We then, in the ERP system, which is Dynamics, actually pulling the data out of that queue, and then we're putting that information into the accounting database, into the customer record, wherever we need to have that information. That was super cheap to implement because it's event-driven, because we didn't have to go and create massive API discovering weird queries against their system, but whenever they have a change, they simply raise an event, we turn around, we grab the data, and then we put that into our system. They also have a flow the other way around. They give us an open API which we can call, and whenever we make an update in our system, whenever we update a customer record, a shipping address, any of those things, we will go and raise the event into their system, and they will go and update there. So we have synchronization between those two systems using an event-driven API. Fantastic. The club used no external help. They have two devs who are usually extending the dynamic system. Their language in which they usually write that application is called AL. That's the language in Dynamics. They had very rudimentary knowledge of C#. It took us, including teaching them how to do those things in C# and how to do Azure Functions and all those things. and how to deal with Service Bus took us 3 weeks. And today, if we did this again, it would take us a week. Absolutely fantastic, optimal integrations case, great. Now, when a ticket is being sold, there's another event, that same event that's being raised is also raised to another company system called Access. And that is actually the turnstiles at the stadium. When you show up with the ticket, they are actually checking, as you're putting the ticket under the reader, they're checking a database. That database is populated also by that event flow. So ticket sold goes into the ERP, also goes into the Access system. Ticket revoked goes here, goes there. Absolutely fantastic case for extensibility using of the ticketing system. And the ticketing system is being extended by the stadium and our ERP system. And the other way around. Love it. Great story. I was super excited when I saw that API show up. Oh, and then I forgot one other flow. Of course, when we are updating our customer information, here, like any of the base data of a customer, we're also raising an event into the single sign-on profile, which sits in the shop system that the club has. So it's practical, fast, and requires very little coordination if we have the metadata and we can go and exchange that. And of course, that's an experience because it requires implementing an open API, requires a bit of plumbing that you have to go and do yourself. I think we can make this even better, but this is already great. So think of what your APIs are. APIs can be calls that you offer for imperative consumption, or you can say, no, my state changes in the system. Someone else can go and act on it, should act on it for integration. So whenever the state in my system changes, I go and raise events so that someone else can go and react to it. And that yields much cheaper integrations. It's a super, super story. I grabbed 3 further use case stories out of our case study folder in Microsoft that are related to Event Hubs and to Event Grid. Just as for you as reference, we're not going to go through them in much detail here. You're also going to get the slide deck so you can go and look at the studies. And there's more, of course, on the case study side with various ways of how people are using eventing and events to build extensible systems, or how they're using events to gather information. So here in Colibri Games, for instance, that scenario, people are playing games on handhelds, and then the handhelds, as people are doing things in games, are emitting individual events. Those events are being put into Event Hubs, are then being analyzed using Stream Analytics, go into data lake storage, and from there are being analyzed for all kinds of various things. So that's kind of learning about the world, we're learning telemetry, things that are happening in real time, and then being able to dashboard them, for instance. In ASOS, here's a system which is using Event Hub for the cold path, getting data from the clickstream on ASOS.com into Event Hub and then into Azure Data Lake Storage using Event Hub's Capture, something I'm going to talk about in the later talk today, but then also putting these events into a service fabric ring in which they're evaluated within milliseconds to basically compute the recommendations which are going to be presented on the next page load for that particular client. And then Bridgestone has a scenario where they're collecting tire information data from vehicles, from trucks, and are putting that into an information portal. All those are things which are done by observing things, basically collecting that information, and then analyzing that information. Okay. After a few practical examples of what that is, and I'm super excited about the soccer scenario. Did I say that? Let's go back to a bit of computer science here. And I just realized I forgot the jacket, so I'm not a proper professor. A signal is the capture of an occurrence during the operation of a software system. So the signal is the payload that you want to distribute. It's not the event. The event is the envelope you wrap around that signal to be able to move it. So the signal is the data you want to communicate. The signal may be encoded in a certain fashion, right? The signal might be in protobuf or in Avro or in whatever format that you, industry-specific format, whatever, right? The signal is the data. The event is the wrapper you put around that signal so that it makes sense in the system and can be transported. It also gives it context, right? The signal says the temperature was 20 degrees. That's what the signal says. That doesn't necessarily make sense without knowing where that comes from, that it is that sensor. So the event basically gives it context. It says it was that sensor that sent that. And sometimes the sensor doesn't even know where it is, and that's actually pretty common in IoT scenarios, but rather the system that's built around it will then know and will give that signal context. So the event is the context that's being put around that signal. An event stream is a sequence of events that are from the same source, typically labeled with something like an order key or a partition key or something like that. So they're all related events. That's an event stream. You can now go and take a bundle of these event streams and put them onto a partition, for instance, in Kafka or in Event Hubs or any of these infrastructures. But those bundles don't create much of a relationship between those streams. So the stream, the thing that actually matters to the application is really an ordered set of events from the same source. That is typically what matters. And whether that stream sits on partition 1 or partition 3 of an Event Hub has no semantic meaning. It's simply more lanes to allow for more throughput. So event stream related to one source. A job is not an event. A job is like a signal. It's data you want to go and convey to someone else, but with that, you want to tell them something to do. You have an intent that goes with it. With an event, you don't convey an event. You're basically just telling a fact. And someone else can go and do something with that fact. They can volunteer to do something, but they're not required to execute something. So there's a semantic difference, even though the things may look alike. There are tons of signals. And whenever you look into the systems that you write, you will see that there are tons of signals that you are having in your systems that you can then raise. And that might then be interesting for someone to go and build something on top of that you have so far not thought of. The engine oil pressure has been read, a package has been scanned, a package has been delivered, the mouse cursor has moved. The mouse cursor has moved is actually one of my favorites here. The older amongst us will remember there was a time when messaging was literally in your face in Windows. You had messages that had labels on them. WM underscore mouse moved. And then you had a long parameter and a short parameter. And those parameters would tell you where that mouse is. Now, Windows had no idea what you would do with that information. It would just raise that event to you. And then you might, in your application, react to it by making whatever, a little dinosaur which chases the mouse, something useful, right? But Windows and all the GUI systems that exist are at the core event-driven. They don't know what you're going to do with all those events. They tell you, hey, there's a blank area. I know that there's a blank area on the screen now. WM paint, please paint that. The mouse has moved. Someone has clicked a button. These are all opportunities to go and react on them and then do something with it. All of Windows is built on extensibility. It's an extensible shell because it does eventing. And so, exactly like that, you can build your own systems to be extensible and say, something happened. And then someone can go and extend it. Can do something that the original creator of the system hadn't thought of. Like chasing the mouse with a little dinosaur. Events put these signals into context. So here we have a bunch of sensors and there's a building. So we can go and organize those. There's a gas and biohazard sensor, there's a climate sensor, there's a fire and smoke sensor, there's an occupancy sensor. And those sensors are being installed, they have some ID on them, and with that ID they can go and emit information, but there's no further context. So the further context is being created by the system for all those sources. So we organize those things. So we say, okay, so these things sit in a room. That room is inside of a unit. That unit is inside of a floor. That floor is in a building. That building sits on a site. And that site is now being managed by an organization. All of these things are things that the sensor has no sense of. You might go and configure a string in that sensor to emit that context. But ultimately, this is just a construct of our software system that we're building around it. So with that, now every single one of those sensors has a particular path. It sits somewhere in the hierarchy. It has context. When you look at eventing infrastructures, you often see these kinds of hierarchies. It's very prominent in very many applications of, for instance, MQTT, where these kinds of structures actually show up in the topic paths, where the metadata, meaning the context information, actually is being embedded in the topic path. If you were publishing events into a REST-like structure on an HTTP site, in an HTTP web service, you would probably do the same, right? You can go and take these paths that I have in here, right? Or Contoso site, Berlin, building 41, floor 3, unit J, room 4, sensors, occupancy. You can very easily imagine to build a web service controller with ASP.NET or any other framework, which then goes and extracts those parameters out of the path, and then goes and has a very simple function which then takes that event that's being posted and puts that into whatever the backend database is, right? Fairly easy. The interesting thing is now that once we've got these things structured like this, we can also ask interesting questions after we've made probably some aggregation. So that's the following slide. So there are signals that are being transported via events into our system. There are two significant differences of those events. One is immediately actionable. So there's immediately actionable signals. When the fire alarm goes off, there's no grade, there's no 0.5 fire alarm, right? It's fire alarm or not fire alarm, which means you raise it, you catch it, you do something. It's almost like a command. You will feel in your system very obligated to do something about it if that's being raised. It's still not a command. You're still volunteering to do something about it, but you will feel very obligated to do so. So fire alarm. The temperature reading from a temperature sensor is not actionable. And again, that's a matter of really semantics and knowing the context of the system. If you have so here, let's say it's 72 degrees in this room, maybe it's a little bit warmer, at least feels like it. And now your temperature sensor reading, somewhere up here, right, says 76, 78, 72, 73, 68, 78, 80, 76. It'd be silly to go and turn the AC on, on higher power once you see the 80. No, what you do is you observe that over time, and then you say, okay, so the average temperature over the last 5 minutes has crossed the threshold of, and so then you raise the derivative event and says, hey, this temperature has crossed the threshold. It's pretty warm in here. Let's go and turn the AC on for a little bit more. And then you keep observing the temperature, and then you see whether you need to go and further regulate. So those kinds of control actions typically happen on derivative functions of these observations. And you can really think of that as like in calculus, right? You try to find the 0 points, and those are derivative functions. That's the same thing here, right? You have a derivative function, and once that derivative function basically fires, if that detects a signal, detects a value crossing the threshold, then that's when you raise an event. And that event then is immediately actionable. Those also have then different infrastructures, as we will learn. Okay, so once we have context, and once we can distinguish between immediately actionable things and things that you rather observe and then analyze, and then take action on derivatives of them, we can answer interesting questions, purely based on the event stream. We can tell whether there are people in room 41 3J4, and that is because we have an occupancy sensor which has reported that fact, and we can now go and basically look into a database which has captured that information, the last value that has been written, and there we are. What room is unoccupied in building 41? That's also something we can learn. So we can learn all the answers to all those questions by simply observing what the building is telling us through all those sensors. And some of those questions are answered by the data delivered by a single event, and some of the answers of those questions come out of aggregations. And the context for each sensor tells us exactly where that is and how we can go and correlate things. In messaging and eventing, we have come up with an interesting parallel development in terms of architectural pieces that you can go and use. If you look at AWS, if you look at Google, if you look at the open source ecosystem, if you look at what we do, you find the same kinds of services again and again and again. That is no accident because they do different things. So a discrete event router, as we have it with EventGrid, and AWS has it with EventBridge, and then Knative has eventing, and there's some other products that do the same thing. They are there to go and take events and distribute those events usually in a push distribution fashion. So you have events that you want to go and raise, you take that infrastructure, and that infrastructure will go and, for instance, call a webhook for you. Why do those things exist? You could certainly call the webhook yourself. They are taking effectively the complexity of calling a webhook from you. You call the thing is always there. It's not going to fail on you. We try hard. We try harder than the target usually does. And then you can basically hook up the destination. If the destination is down, too busy, whatever, we will try for 24 hours to get that event delivered. So we take that burden off your shoulders. Also, if multiple parties are interested in that event, of course, the whole subscription management is something that we do, and we integrate with other infrastructures. Like we can also go and push the message to a queue. We can push the message to an event hub. So we create effectively a flexibility for your events that you can then distribute as you like, which is more flexible than calling the webhooks yourself. Like all the infrastructure pieces that you have to go and build up to create that sort of extensibility, manage the credentials and URIs and subscriptions and all that stuff. That's all done for you. So that's what EventBridge is for. Push, typically. That only works for discrete events, for events which are independent of each other. So they don't depend on the event before and after them. They don't form streams, because if you push, then you will typically push into something like a web farm, right, into a web endpoint, and you do this using HTTP, webhooks, which means you can't preserve order. So logically, right, all those things are independent of each other. There are events like this customer record has changed. The packet has been delivered. All those things are individual actionable events. The temperature reading of a sensor individually, not a good candidate, because it's not actionable per se. Again, it's always the semantics of the individual event, of the particular context, to determine whether something is immediately actionable or it's not. Then there are queues and pub/sub brokers. Those are for jobs. What a queue is, the top feature of a queue, the top feature of a message queue is that it gives you exclusive ownership of one message. Which means if you have a job and that job needs to be done, put it into a queue, and then you have multiple processors which are trying to get that job done because you want to go and scale. And the top feature of the queue is that if one party gets that job, nobody else will get that job. And only when that party says, I'm willing to give that job back, release it, sorry, I couldn't get this done, or I'm accepting it, I'm settling it basically, I'm done with it, then that message is getting either archived or deleted. But exclusive ownership is the top feature of a queue. It's not the order, it's not any of the other criteria, it gives exclusive ownership. because a job typically is being done once, and none of the infrastructures that do eventing do that because they're for PubSub. Therefore, send an event and let anybody go who's interested see it. You can't do that with a job because for that job, you will have one party which should go and execute it. You don't want to go and double charge your credit card. Very different infrastructure. The queue keeps track of the life cycle of every message. Eventing infrastructure does not. Azure Service Bus, AWS SQS, Google PubSub, Apache ActiveMQ, RabbitMQ, IBM MQ, all of those are queue brokers which are doing that part. Then there are event stream engines. What those event stream engines do is they log streams of events that are related. You can go and label them with keys so that they are preserved in order, and they're typically mapped onto partitions so you can go and run very, very large torrents of these events. Just to give you a sense of what the relative dimensions are. So in Azure Messaging, we currently do about 7 trillion requests per day, right? Of those, 90% are event hubs, are event streams. There's an overwhelming majority of traffic is event information, is information that's being distributed. It's not jobs. That infrastructure therefore needs to be super fast, efficient, and doesn't have a lot of features per se, but it's really just there to go and capture information. So I'm going to talk about that in more detail. And then there's event stream aggregators, and event stream aggregators take data, look at it in more detail, and then go and produce output based on them. But they are kind of attached to these event stream engines as the compute aspect of them, if you will. Okay, this is very important. Event streaming is not modern and queues are not traditional. I see a lot of that nonsense going around every day. People are saying, oh, we have been using whatever, ActiveMQ, but now we're doing something modern and we're using Kafka. You are literally switching the architecture from a queue-based thing, which is doing jobs, to an event-based thing, which is distributing data. If you think that's smart, okay, but then make sure that you actually have the right infrastructure for the job. And so we see a lot of this. People who are then saying, oh, there's a shiny new thing, let's go and use the shiny new thing without being really clear what they're doing. Typically, sophisticated applications use both because the things that they're doing are different in different scenarios. Modern apps usually use queue-based messaging, RPC, and extensibility both, as I explained in the examples already. So there's direct interactions between services, that's all imperative flows. And then there's extensibility, which is all eventing flows. That's typically how those things end up. Of course, you have eventing in your own systems as well, and you bind those things together, but you can also look at those as extensions. All right, let's double click into event streams. Event streams and these event stream engines are special because they solve a particular problem, and that is timeliness. Securities markets show this nicely in a very prominent way. That's why I'm picking data from NASDAQ here. But that's actually true for many event streams. In many event streams, the freshness of events actually matters. And nowhere more pronounced than in securities markets. So in NASDAQ, and then through resellers effectively like Bloomberg, you can buy market data that is super expensive while it's 3, 4, 10 seconds old. If it's 15 minutes old, it's nearly worthless for trading. And so for algorithmic trading, freshness of events is really important. There are products that are being created and offered and closed on Wall Street, which exist for less than 500 milliseconds. All algorithmic trading. You cannot participate in those markets unless you have a data center on Wall Street. And you're connected to the fiber that reaches across the street. You can't. Because latencies matter extremely. Freshness is super important. So there are companies, Solus, TIBCO, who made most of their money, most of their fortune comes out of being super, super, super fast. Sometimes having appliances which you can install, which are highly optimized for super high, low latency traffic. It's all volatile. It's all in memory because if it doesn't happen in milliseconds, microseconds, then forget it. So event data value is super high when fresh, and that's kind of super extreme in financial markets, but we see this everywhere else. That also means that we need to have infrastructure which is specialized on it. So the cases of these Solace, TIBCO, et cetera, infrastructures are super extreme and not the common case. And of course, in the cloud, the world is a bit different, but the pattern is true for many scenarios. So what emerged were these infrastructures which are called, what I call the pattern catching rain, meaning events come in, and then what you do with that torrent of events, you first start to organize it. You just try to get those events captured and on disk. That's the most important thing. Take that big torrent of events, telemetry that comes out of cars, telemetry that comes out of factory processes, telemetry that comes out of click streams from websites, all of that, just take it and just get it on disk. And now, once you have it on disk, once you have it captured, once you have it organized kind of in these partition streams, then, because freshness matters, then you want to go and process that raw data in parallel, which means you want to go and visualize it, you want to go and archive it, but you want to archive it in a way that it can be used for batch processing in very little time with very little delay. You want to go and take some action on it. You want to do real time, derivative signals, all those things, but you want to do this in very minimal, time distance from when those events occurred. So that's why all those event brokers have the ability to provide multiple consumer groups with that stream data. But because speed matters, the event engines per se don't have a lot of features in them. There's no filtering. There's very little that's inside of them. And, between Kafka and Pulsar and Event Hubs and Kinesis, there's enormous competition. Still, none of us are breaking into jail, as I say, to go and add kind of these super expensive features into those event stream engines, because that's not the purpose of them, right? They're catching rain and are getting the events on disk, and then are moving those events as fast as they can. The event streams are providing information inside of the event log store, inside of the event hub, in a matter that's organized primarily by time, right? You have a event stream where the primary index of that table, if you want to look at it like this, is the time axis. That's what they're organized by. And for everything that's real time, that's okay, because you are looking at effectively a set of contexts and they're being played onto you. You're basically sitting in the middle of that torrent with your compute engine. Let that be an analytics engine like Stream Analytics or your own code, and the data is coming to you. And now you're seeing those events, and you're effectively getting those. The contexts are being given to you, and you're handling those contexts. But it's always effectively operating on the time axis. Once that data ages, you need more criteria. In that car fleet here, right, in real time, you will want to know, where are those vehicles? Are they healthy? Do we see any alarms in fleet management? Once a car is in the shop and something broke, and you have telemetry that you might be able to look at, you will say, so this vehicle on this sensor, maybe we're kind of finding an anomaly here, so let's go look. But you're now no longer just looking at the time axis. You're actually looking for 1, 2, 3, 4 criteria to then go and look at that information. Which means that you better have that information stored in a real database. It's no longer good to have it stored in an event stream engine. There's architectural disagreement between, for instance, us and Confluent, just to name a company. We believe that you should store these events as they come in the database. Maybe that also has to do with the fact that we have databases. In a Kafka architecture, as promoted by Confluent, for instance, all the data gets pulled out of Kafka all the time. It looks like a database, and then you run it through an in-memory, effectively, query processor that then can go and cache information in materialized views. But events are views of history. They never change, which means if you go and take the events and put them into a database, that will always be true. You don't have to go and put data into a cache and then throw the cache away. You can just go and put the data into a database and be done with it, and then index it appropriately. So we have an architectural circuit breaker in our system, in that we allow on Event Hubs only for 7 days, or in the extreme, in Event Hubs Premium, Event Hubs Dedicated, up to 90 days of retention. But you cannot retain for all time, because we think it's harmful to do event sourcing forever, right? To go and retain all the events you ever had in an event store and then only be able to go and access it by the time index. Because while event sourcing, building databases from the beginning of time on the event stream always looks like a good idea, 3 years down the road, it no longer does if you have significant data, right? If you have a database that's sized to the request rate that you currently have in your system, and now you need to go and rebuild a database with 3 years worth of transactions, when do you want to be done? That's one of those things. So we believe that the event streams really need to get indexed and need to be put into the database. And if you want to go and build a new database, then you do that using a database transformation, and then you can start applying new events. So event sourcing, yes, but from fresh data, and then you do conversions. I told you about the James Webb Space Telescope. This is the slide, ASH2. The James Webb Space Telescope has a very fancy optical instrument, which is super complicated. I don't understand. What I understand, though, is that the big mirror captures lots of light and then reflects that into a small mirror, the second mirror, which kind of sits on the front of it, which then reflects it into a third mirror, which sits here in the optical instrument, in the instrument cluster. So this is the fancy thing you see. That's the thing you see in front of it. And then it reflects that into the optical instrument cluster. That is Event Hubs. Event Hubs captures events, it doesn't look at them. It doesn't consider them. What it just does is it makes sure that those are captures, that they're organized, and that's what it does with them. It never looks at the signals. It never looks at the payload, right? The payload, the information, the signal is untouched. And that would be harmful if you did that in a telescope, if you had any filtering or any fancy stuff in a telescope, because you have a spectrometer, you have various imagers. There's, I think, 4 or 5 major science instruments in the James Webb Space Telescope. And with a mirror mechanism, you can basically go and take that input stream and just point them at the various different instruments so that they can get an unchanged view. So this is the same thing, right? You have an event stream. The event stream comes in. We don't change it. We don't do anything to it. We don't look at the payloads. We don't transform them. We also don't slow it down. But what we do is we say, you have 1, 2, 3, 10 jobs, which are all the science instruments, which want to go and look into that data. Now, the James Webb Space Telescope hangs in space, and it has a transfer rate of 1 megabyte per second. That's allowed. Right? It can do a little bit more, but it has 2 time windows during the day, during which data can be transferred. But for a science experiment, the maximum transfer rate is just under 1 megabyte per second, which means that this enormous enormous amount of first analog and then converted to digital information cannot be transferred. Which means what we need to do is we need to do analytics on that information stream in the Space Telescope. That's where a lot of the science happens. And then a substrate of that information is being sent down to Earth and goes into the database. The same is true for many architectures, stream architectures. You have a stream analytics engine that sits right behind Event Hubs, for instance, which goes and takes the information stream and creates an aggregation of it, and only the aggregation is then sent down, and the raw events sometimes are not even kept. and then that's being put into a database. There's what I call, and I'm just borrowing a term here from astrophysics, there's something I call the event horizon. And the event horizon is where that raw event stream no longer has the impulse given by the producers, but it's being turned into a pre-processed set of information data that is now retrieved using queries. At that horizon, kind of at that boundary, you turn from query, from stream processing, from flows into query processing. And we see that a lot. So as you put the data into a database, and then you go and maybe still go and look at the time series, but you go and query that data because of some certain interest. And that's where you also need to have that indexing, because then your approach to that data changes. One, on the left side, it's driven by that impulse by the producer. Once it hits that horizon, once it hits basically the boundary where the events are being opened, looked at, and considered, and then being put into a storage or database or whatever, then that impulse is effectively gone, absorbed, and from there on, you basically start querying that data. So the flow direction also is impacted by this. I'm going to show you something. Our very capable PM, Sid, I'm just going to show you a YouTube video because he did that demo much better. I tried to also do that demo, but my demo didn't come out as good as his, so I'm going to talk to his demo. So you have an event hub here, and that event hub is being populated by data. That is completely downloadable, that demo. That's nice. That's a tutorial that you can run. So that's data in here, and that event hub. What we're now doing is in the event hub's portal, we're clicking process data, and we're now picking the option to go and put the data into Parquet format. Okay? Now we can go and create a new stream analytics job that is happening directly on the event hub, directly where you are, and then we're going to call this Contoso capture. Okay, now you see the event hub already being pre-populated. We need to tell it what the serialization format is of the events as JSON. And so we can go and change also the authentication method. We'll be able to go and set this to managed identities, or the managed identity if you want to, but we're using the connection string here, and then we connect. And what it will now do is it's going to go in and sample the data that's already in the event hub. So it's looking at the data that it finds in the event hub already as stored events. You can now go and edit the names, or you can go and remove elements. You can go and correct the data type if you need to. And then you go and configure the target where that goes, and that's in this case an Azure Data Lake Storage Gen 2, picking a subscription where that storage account lives. It's also, again, pre-populating the necessary information to go and get there, picking a container that we have created in that data lake, and then we're going to go and connect. First we're going to go and put the directory path pattern because we're populating effectively blob store. So we're going to say here that we want to go and organize by date and time. And then we're going to pick the Parquet serialization format in which it's going to be written. And then there's some parameters for how long, how big those packets are going to be, also impacting what the latency to the storage system will be. And then we go and connect that up. And now with that, we can now go and save that stream. With that, we've created, without writing any code, a direct path to go and get that data into Data Lake Gen 2 with the ability to actually go and also manipulate the flow. We can, with that no-code editor, also do aggregations and some other operations. Basically, everything that Stream Analytics can do on that path, we can do here in that no-code experience. Super easy to go and set up. And then we can also configure here the number of streaming units, and then we start the job, and then that job starts, and then starts basically taking the information that's in the event hub and shovels that into the data lake. We have the same functionality for SQL, for Cosmos DB. So if you want to create projections into databases with or without aggregation, you can do this very easily now as effectively part directly of the Event Hub's experience without writing any code. So now that job is running. You can also go and delete that from here and manage that from here. And now I think we will go and take a look at the results of that. Here we go. Okay. So that's the storage account or the data lake account now. And you will find that under the date and the day, there will now be these Parquet files, which have been written based on that. So that's the output of that job. And now what are you going to do with those Parquet files? Parquet is a format, columnar storage format, which is understood by many analytics engines. So here we're now in Synapse Analytics, and we'll have a little data frame loaded basically from that address. So now this is actually has the Spark engine look at that storage account, which will now go and basically go and grab the information now this has executed. And with that data frame, we can now go and take a look at more details of that. For instance, we can go and take a look at how many records have already been imported into that record, into that thing. So it's now running, executing. This is Synapse Analytics running Spark. And it goes and then shows whatever 1,825 of these records have already been imported at that point. We can also go and show here the schema that has now been inferred basically by the Spark engine for the data that is in these Parquet archives. And then finally, we can also go and take a look at some of the record. And here we're going to pick the first 10 of them and execute that. Okay. So, and that shows that information. So this is effectively now in a query engine, which is very capable. SID then keeps going and also shows the same thing in SQL. We don't have to go and take a look at that now. So that's something that will also, you will find linked from my resource page if you want to go and see that demo again. That's the great thing about using videos, is that you can actually go and take a look at that once more and pause, and also look at how you can go and do this yourself in the portal. What we looked at so far is mostly kind of the event is being raised, it goes into Event Hub, and then it's being processed in some way. So it's more like, and that's most examples show, right? It goes into some infrastructure and then gets handled there. What we see more and more of in applications is that those events actually take journeys. So they are being raised somewhere in an IoT device, or they are somewhere on a website, and then they take a journey through multiple hubs. They start in IoT, then they go through stream analytics, are being analyzed, are being forwarded into an Event Hub, are then being kind of picked up by some processor, which is then causing a workflow to happen. But then at the same time, they're also being put into a dashboard. So there's like the same event is causing multiple things to happen, is also routed forward. That is becoming super, super common. The problem we have with that, for us as infrastructure people, but also for you as users, is that not all those paths are alike. Some of those are MQTT, some of those are HTTP, some of those are AMQP, so all the protocols are different. And event, I just gave you a framework for how to think about events, but that doesn't mean anything yet in concrete terms. So what we did about 4 years ago is we got together with a bunch of other people, like for Google and SAP and Solace and others, and IBM, and said, we really need to have a common way how to think about events, what an event is. We used to have something like a common envelope format, if you will, for messages as a standards approach. Soap in XML. People are laughing. That's okay. I feel your scars. And that tried to boil the ocean, and that sank the ship. But the commonality is something that is really important. So we said, okay, we're going to do something that is kind of reeks of this soap, but it's more concrete, and it's not trying to be so ambitious, and just wants to go and describe an event, but it wants to go and describe an event in all kinds of protocols. And not invent a new protocol, not try to be a protocol. We're just going to be humble and try to just define what an event is. And that is working. So you see cloud events more and more. And what it tries to do is you have a producer. The producer is creating an event that is being sent using MQTT, for instance, goes into a field gateway. From there, gets forwarded into a cloud-based endpoint or cloud-based endpoints, but using different protocols, which may then go and take that same event and forward it. So how can we make sure that that same semantic, the same event is being preserved, even though it runs through multiple protocols? We have to go and figure, and how can we make sure that all of that infrastructure, right, understands what that event means without having to peek into the payload, without constraining it to JSON? Because we know that those events may carry OPCOA binary, or Avro, or Parquet, right? All of these encodings are valuable and important for if you send a lot of data around, but we want to have a common envelope around them so we can go and route them. So how does that work? So we created cloud events. Cloud events is a definition of, an abstract definition of an event. Is effectively an information model that says an event has an identifier, it has a time at which it was created, it has a type, it has a source where it came from, it has a subject, what it is about, it carries some content, so it has a data content type, right? And then it carries data. And that's it. That's the common definition of what an event is. And of course, we define in that spec, we define what that is. And then those common properties are then mapped onto various different transports. And we have a mode of encoding that event completely in Avro and in JSON and in AMQP encodings and in protobuf. Or we can go and take that event, explode it, flatten it out onto the transport frames of various transports. So for instance, with HTTP, we are able to take a cloud event and map that cloud event straight onto an HTTP message where the attributes of the cloud event become headers in HTTP, which means you can take any application and make it cloud events aware. You can make any webhook cloud events aware by just adding the extra attributes. And what we also didn't do is we didn't go and create hard semantics around the event use around this. So the HTTP binding says how you map it to the frame, but it's not particular about whether you should use pose or put or get or whatever method. We have an extra webhook spec, which then proposes that you use post for a webhook implementation, but that's not required. So we intentionally try to get out of the way of the semantics of the particular protocols. We just humbly say, here's how you map this onto your transport frame, and then you do whatever you want with that protocol. And we also made sure with the APIs, there's also APIs that go with it, SDKs, that we never obscure the features of the respective infrastructures that we map cloud events to. So we're trying to be humble, not try to invent anything really new, but really just humbly contribute commonality for events to the world of eventing. And that seems to be catching on, which is great. Currently, we're doing some extra work on further specs. This is the complex we call discovery in the message catalog. That's also the things that they already show up in several products in the industry. So first is a notion of a schema registry. We have encoded data structures, right? And those encoded data structures are found in messages, but they are then also found in a storage file or then also found in a business app. You just saw an example of this, right? There's an event that carries data. That data now propagated through Stream Analytics, which understood it, through to the database, the data lake, through to the application, which reads that information. Now, JSON is self-describing. So that structure kind of is embedded in the structure, but it's also terribly inefficient. So with encodings like Avro or protobuf, that metadata is external and sits in external files. Now, they need to be managed somewhere. They need to be referenceable. They need to be visible to the producer and the consumer. So you have these things called schema registries, which allow you to kind of share these schemas. And so what we're doing is we're first formalizing in a standard way in CNCF what a schema registry API looks like. Because there are schema registries, but there's no standard for them. So we said, okay, we're going to go build one. Then we want to have a way to define patterns, templates for messages. We want to be able to say, here's a service, and that service is raising these 5 events. What's the shape of those events? Not the concrete event, but really, what's the pattern for that event? How do we know that the file store will raise the blob created event? There's got to be some documentation for it. You find this today typically documented with those services, but there's no formal machine readable way to do this, to document them. So that's what the message catalog does. The message catalog has a message definition group, which captures message definitions and see those as effectively the interface, the referenceable interface of these for those messages. Now, the great thing is a message definition group has a URL. It can also be put into a document, which means if you can go and take a queue or a stream and simply associate that with that URI, you now have metadata that says, in this queue, the following messages are allowed. Or from this queue, you can expect the following messages. That is super trivial, now that I said it, but interestingly, that doesn't exist. So now it will. So now you'll be able to go and say, there are 5 types of messages which come out of this AMQP queue. Look at this document, because we're defining that now with a bunch of companies. And then in the system, you will also want to understand, as I just said, there's a subscriber endpoint, there's a publisher endpoint, there's a producer endpoint, there's a consumer endpoint, which means around Azure, for instance, there are several services which all can emit events. Which are those? And what comes out of those? So what we're building is a discovery service, and defining that with multiple companies, where you can go and walk up to an endpoint and say, I want to receive this event. Who makes this event available? Or you can look around and see who's raising events in your system, and those will be populated by the system itself. Azure has native things that are raising events and also things that you can go and build. So that's the current work we're doing in CNCF together, and those will materialize in the end in products. So for all of this, we have a ton of services. Already we have the schema registry that sits inside of Event Hubs. We have Event Grid. We have Service Bus queues, and then we have all these other services which kind of are integrated with the core messaging fleet. And then we have a ton of adapters which are in Azure Logic Apps. So Azure is already an event-driven platform, has a lot of these flow capabilities already, and we're working on getting that better integrated, more tightly put together, so that this doesn't only show up here in these slides, but you actually also see that in the product materialize more than you probably see this now if you are not reading the documentation. So lots of eventing here. There will be a lot more. We're building on new experiences into Visual Studio, into Visual Studio Code. You're going to see more runtime support for eventing and more things that raise cloud events. And I can only encourage you to look at your own applications and see how you can go and raise events to make your own applications more extensible. So with that, I actually landed on time, surprising myself. Again, mind that I'm being paid by exclusively the results of this survey. And so that's the resource. You can go to github.com, Clemens V Messaging. That's where you find all the links. They will also find the slides for this talk. And with that, thank you for coming.